AR means autoregressive. That's what we mean by AR. Okay. Now you are welcome to this topic. Now, last time I talked about the two important concepts in time series analysis, autocorrelation and stationarity, and I also talk about white noise model. Okay. And you know what? I will quickly remind you because these are fundamental, these are very crucial when it comes to time series analysis. Now, in time series, we got assumptions of stationarity. And what stationarity means is uh, constant mean and constant variance over time. Okay, I'm going to say that again. Do you know that the constant mean and constant variance over time actually, the moment that hold, that we're actually going to say that the stationarity assumption hold. And let me tell you this. I remember I told you the significance of white noise model the last time we met. The white noise model has actually, play two roles, two major roles. Number one, it is used as a baseline comparison. Okay, you know, we use it as a benchmark if we really want to evaluate the presence of trend or the presence of a pattern, okay, in time series data. Okay, situation where if your model is entirely white noise, then it means your model is unpredictable. We are not able to detect signal. We're not able to detect, trend, and there is no pattern. And because of that, no correlation exists. Okay. So the white noise properties of having a constant mean, a constant variance, and no autocorrelation is a fundamental concept in the reason why that will enable us to understand, the unpredictability and randomness in scientific and engineering field. Okay, and you know what? Uh, Another role the white noise model play is that if the random part of a model, of a time series model, is a white noise, then that's a good model. I'm going to say that again. If a random part of a time series model, okay, is a white noise, then that model is a good model. What we mean is that the model has succeeded in capturing the relationship, the trend, okay, in the time series data. Okay, now, you know what I want to do now? I actually want to go into, I want to introduce what assumption that we place on a white noise. Okay, take a look at this guy now. Okay, in time series here, WT is a white noise because we believe it's going to follow normal distribution, which means zero, and the variance sigma square W. Okay, that is for the white noise. Now, if I specify a model, a time series model, every time series model, we always have what I call the WT, which is the random part of a model. For time series, the first part is going to be signal. The second part is the noise. What we normally want to do is when we have data set, a time series data, every time series data is contaminated. What do we need to do? We normally want to filter out the noise. When you are able to filter out the noise, then you'll be able to have the signal. You'll be able to capture the relationship that exists. Okay. Now, this is similar to the way we specify linear regression model. You know, in the linear regression model where you are relating y a response variable y to an explanatory variable s, okay, you're actually going to see that we also have the deterministic part. We call this a deterministic part, and we call this a random part. So the deterministic part in linear regression is synonymous with signal in time series. I'm going to say that again. The deterministic part in linear regression is synonymous with signal in time series model. I just want you to see the connection they have. For time series model, we refer to error as a noise. In linear regression, we call it error, we call it residual. Does that make sense to everyone? Okay. Now, I want to move right now. Now, let's have an example here. Okay. The example we are actually having here is, suppose yt equal to this. You know, anytime you see stuff like this, that is an AR1, autoregressive model of order 1. Why do we call it autoregressive model of order 1? Because they are one lag apart. The moment you see yt and yt minus 1, that is one lag apart. Okay. Now, and that is going to be called autoregressive model of oh, sorry. Oh, oh, give me 1 second. I think in a way, let me see. Give me 1 second. I'm going to stop my share now. I think I'm going to report this to tech. Give me 1 second. Let's see. Oh, okay, but I'm not able to see. Okay, I think I'm gonna, let me remove that. We're not gonna use that. Um, okay, so can you confirm if you are still seeing what I'm projecting, everyone? Oh, you're still seeing that, right? Okay. Now, if you take a look at what I have, because we're relating yt to yt minus 1, and that actually indicates an AR of order 1. Now, for instance, I want to talk about the revenue for the daily revenue from ice cream. Okay. Now, if this is the revenue that come today, we want to believe that out of the $102 that they make, $100 is a contribution from what happened a day before, and $2 is actually the one from the noise. Take a look at that. So, which is adding signal to noise, that will give you the observed YT. And that was why I said every time series data point is contaminated. Okay, that's what I'm trying to show there. But you know what? I'll quickly move. The other time, let's revisit a white noise model so that you'll be able to differentiate between a white noise model and autoregressive model. This is a white noise model. You can see this, a white noise model is a model that is entirely white noise, no signal. Does that mean saying there's no signal here? Okay, WT is the white noise and C is a constant. Now, if your model is a white noise, you know what that means? If your model is a white noise, then it means we cannot make a prediction. That's what it means. It's unpredictable. That's what it means. Now, I want you to see if I simulate time series data with this, where my WT is from a standard normal distribution, I'm actually going to, if I generate a time plot, I'm going to have this guy. If I'm assuming this to be a daily sleeping hours for Kazim, then what I'm trying to tell the world is that Kazim sleeping hours cannot be predicted because Kazim's model for that is entirely white noise. Now, if I want to find the average of YT, you know what is happening now. You are given a white noise model. You are given a white noise model. Please, I need you to pay attention. Whenever they give you a white noise model, you're going to see something that look like that. They're going to tell you the way your data is generated. WT here follow normal distribution with a mean 0 and a variance 1. Now, you know what I want to do now? I want to find the average of Kazim's sleeping hours, which means I want to find the expected value of YT. I also want to find the variance of YT. That's what I want to do here. Take a look at this. Okay? If I want to find the expected value of YT, don't forget YT equal to WT plus 8. I'm also going to find expectation of WT plus 8. Expectation of WT plus, the expectation of a constant is a constant. That's why you see 8 here. Okay? You know, that was why you actually see here. Here we are assuming expectation of a constant is a constant. Now, can somebody tell me, what is the expected value of WT? And how am I going to know that? Whether in person or online, how do I figure out this guy? Expected value of WT. Can somebody tell me? What is it going to be? 0. Send me a message for extra credit. Do you know how I know that it's going to be 0? I need you, if you want to know, you're going to come, you need to come here. Do you see that guy? That first number is mean. It means expected value of WT. Okay, so this guy implies expected value of WT equal to 0. And the variance, please always make sure you look whenever you have a specification like that, they are giving you the mean and the variance of a WT with that specification. Do you see that now? Expected value of WT is 0. The variance of WT is 1 based on the specification here. Pay attention to the specification. It could change. Now, I want to plug in, definitely here, I'm going to plug in 0, right? What is 0 plus 8? 0 plus 8 is going to be 8. Now, I want to do the same thing, finding the variance. Okay? If I want to find the variance of YT, then I want to find, and what is YT? YT is WT plus 8. The variance of, don't forget the WT is a random variable. 8 is a constant. Okay? When I have a variable added to a constant and I want to figure out the variance, the constant is going to go away. I'm only going to have the variance of WT. And based on the specification that you have before, the variance of WT equal to 1. Okay? Now, I also want to tell you, whenever we are dealing with a white noise model, autocorrelation at lag 1, at lag 2, at whatever lag is going to be equal to 0. We know autocorrelation, this guy here means autocorrelation at lag 1. This guy here means autocorrelation at lag 2. And so on like that, up to autocorrelation at lag k. Now for white noise model, autocorrelation for at any lag is 0. You know what I mean? No connection between now and the past. That's what it means. If there's no connection between now and the past, then your model is a white noise. Does that make sense? Okay. Now that you understand the white noise model, which is the simplest model in time series, then we now want to move to a model that is not white noise. I want to welcome you to AR1 model. AR means autoregressive. You know, autoregressive is like you actually going backward. You want to relate what is happening now to what has happened before. When I say autoregressive model of order one, then if the unit of time is day, okay, then I'm relating today with yesterday. If unit of time is months, I'm relating, we're in July now, or I'm relating that to June. Does that make sense? Okay. And let me now, which means I actually using the most recent pass. This is going to be the most recent pass. I want to use it to predict the current. The current is YT. What I actually record at this time T relatively, and I'm relating that to the immediate pass. Immediate pass is YT minus 1. Do you know that if I'm doing this, if I'm relating YT to YT minus 2, that is no longer a arrow of order 1, but this is going to be called a arrow of order 2. Okay, whenever if I'm looking at this relationship between YT and YT minus 2, you know what that means. I'm relating current with you know past like a day before, if the unit of time is day. Does that make sense? But right now I want us to focus on the AR1, where we actually want to use information about immediate past to explain the current. And how do we specify the model? Please, I need you to pay attention right now. I'm actually going to show you we got two ways of specifying an arrow of order 1. Do you see that? Oh, give me 1 second. I think, do you see that? That's an arrow 1. Right now, we don't know C0. We don't know C1. Does that make sense? That is looking like a simple linear regression. The only difference between this and simple linear regression is that in simple linear regression, our YT is just Y. Our YT minus 1, can somebody tell me? What do we normally denote in simple linear regression? Instead of YT minus 1, what do we normally have? Can somebody, whether in person or online? Those of you online, can you hear me? Okay. Now, if you can hear me, I also need you to answer the question. I actually trying to say something right now about what you're seeing here. Okay. I said relate this guy. How is it different from simple linear regression? YT in simple linear regression is Y. And the question is, what does YT minus 1 represent in simple linear regression? Those of you that are attending online, please, you can only attend this with your video on. With your video on. No, I can see some students right now, they are actually, they don't put on their video. I'm not going to allow that in the future. So because some students can join online and they can be away from their laptop. So those of you that are attending now, put on your video. I'm seeing 3 students, okay, 2 more students. Oh, okay. Are those that did not put on their video, are they the one in class here? Oh, good job. Good job. Okay, I can see. Sorry about that. Okay, now back to my question on the because I'm gonna award extra credit. You know, in that model now, YT represent Y in simple linear regression. My question is, what does YT minus 1 represent in simple linear regression? Want to answer the question? X. Good job. Send me a message for extra credit. It's X. Okay? So in simple linear regression, you're going to have this. Y. Please, I just wanted to see the connection. Y, we normally write beta naught, okay, plus beta 1x, okay, plus the error. I just wanted to cite it different. Okay? So in simple linear regression, we're not focusing on time. Okay? In time series analysis, the focus is on time. That's why it's called time series. Okay, now, and whenever they specify the model, I'm talking about AR1 now, okay, there's always going to be a specification for the WT. Do you see that? Do you see that? They're always going to give you the specification because we assume WT must follow normal distribution. They're going to show you what the mean is and what the variance is. Okay, and if you take a look at this now, it means we've already found, of course, I'm going to show you how to estimate parameter in a time series model. What they are trying to tell you now, your C naught has been found to be 0.8. Your C1 has been found to be 0.9. Okay, I'm still going to walk you through how to estimate parameters in a time series model. Okay, now I'm going to show you another specification right now. Okay, alternatively, this is another specification. If you are attending the lecture in person, you may not necessarily put on your video if you join the Zoom, okay? Because I'm seeing you already. Thank you. Okay, now this is another way to specify AR1. Please take a look at that. What is the difference between the first specification and the second specification? The second specification has mu. Do you see this guy? That's what we call mean. It has a mean in it. Okay. And take a look at this guy now. Okay. It's actually, which means we are having mean as part of the model. Okay. So we got two ways to specify the AR of order 1. Okay. In either of the specification, don't forget, we're always going to say WT. We're going to specify the distribution of WT. Now, I've given you two different ways of specifying autoregressive model of order 1. Now, the next thing that I actually want to do now is I want to focus on this guy now. Okay. Let's say we have that guy. They gave you this guy. I'm seeing a lot of exam questions here. I need you to pay attention, okay? Now you have this guy, and they give you this specification. You know what that specification means? It means the mean is 0. The variance of WT is 0.19. Does that make sense? If you take a look at that specification, because without this specification, there's no way I will be able to answer a question that has to do with finding expected value of YT. Okay, how do I find expected value of YT? Please, I need you to pay attention. I want to find the expected value of YT now. Okay, I want to find the expected value of YT. Okay, what I'm going to do, take a look at this. Can you see that? Expected value of YT. What is YT? Because YT is this. They gave us the model, YT to be that. Is there anybody that want to ask a question on that? Now, what am I going to do? I will use the expectation here to multiply whatever I said in the parentheses. And expectation of a constant is a constant, and I'm actually going to have this guy. Is there anyone who doesn't understand how I move from here to here? Is there anyone who doesn't understand that? Okay. Now, you know what I'm going to do? What is the expected value of WT? Okay, they've given us here is 0. If you look at the specification, do you see the specification? Expected value of WT equal to 0. What are we left with? If I plug in 0 there now, I'm going to be left with this guy. Any question? I'm only going to be left with that guy. Is there any question? Or now I got there because expectation of WT equal to 0. Because they've already, I told you, if you look at the specification of WT, where they specify normal distribution, the first 0 means the first value there means expectation of the random variable. The second value will be the variance of the random variable. Now we are here now. Please, I need you to pay attention. We are here now. Okay, we are here now. But do you know what we want? Do you know moving forward, we're going to consider assumptions of stationarity. In the assumption of stationarity, what do we say? We said the mean have to be constant over time. You know what I mean? The mean of yesterday has to be the same as the mean of today. That is why you see expected value of YT equal expected value of YT minus 1. Does that make sense? That is applying or invoking stationarity assumption that mean is constant over time. You know when that happens? You know what I'm going to do? I'm actually, wherever I see expected value of YT minus 1, I'm going to plug in expected value of YT. Then from here, I'm here now. Any question on how I got there? Because I impose the condition of stationarity. In the condition of stationarity, constant mean has to be constant over time. Mean expected value of YT must be equal to expected value of YT minus 1. Variance constant over time, mean the variance of YT equal to variance of YT minus 1. Now, what am I going to do at this junction? I'm going to solve for expected value of YT. We are back at what you normally do in middle school, where you're going to solve for expected value of YT. Solving for expected value of YT, that will give us 8. Do you know that expected value of YT is also the same thing as the mu? What if I give you this, I give you this guy, and I said, obtain the mu. Mu is the same as the expected value of YT. Is there any question before moving forward on how I got 8? Okay, if there's no question, I'm actually going to move to obtain the variance of YT. Please, I need you to pay attention. Okay, how do I obtain the variance of YT? Okay, what is your YT? Okay, your YT is the model that you're giving. Okay, if you want to go up, okay, do you see? This is your YT, right? Okay, we've derived the expected value of YT right now. We want to derive the variance of YT. Okay, now if I want to derive the variance of YT, oh my God, that is going to be equal to that because the constant is 0.8. When I want to find the variance of a combination that involves the constant, okay, that constant is seen as 0 and I move from here to here. Is there any question moving from there to there? Okay, if there's no question, and I want to figure out the variance of this guy. In figuring out the variance of this guy, you're going to use the variance to multiply each of the term in the parentheses. Okay, that is going to lead us to this, and that will lead us to that. Is there any question on that? Any question? Please ask question. If you don't understand what I'm doing right now, make sure you ask question. Okay, now what do we do the other time? Whenever you are looking at the variance of a constant with a variable, the constant is going to come out and become a squared. Okay, take a look at this. Okay, this is coming from here. Okay, variance of a constant YT minus 1, that constant is going to come out and become a squared. Then you're going to have the variance of YT minus 1. Then, can somebody tell me, how am I going to get the variance of WT? what do I need to do? If I want to get the variance of WT, I need to go back to the specification for WT. Okay, do you see this guy? Do you see that guy? The variance of WT is 0.19 here, according to this specification. I told you when we specify normality, the second value is for the variance, the first value is for the mean. Now, I'm going to plug in for the variance of WT, I'm going to plug in a 0.19. That was why you see this is 0.19. Now, what am I getting now? Okay, now if you pay attention to what we've been doing right now, we are here. Okay, variance of YT equal to that. Now I'm going to use the condition of stationarity again. Okay, what does the condition of stationarity say? Variance have to be the same. Okay, variance yesterday must be the same as the variance today. And that was why you see the variance of YT must be equal to the variance of YT minus 1. Did you catch that? Now, because of that, wherever I see variance of YT minus 1, that will be replaced by variance of YT, and that will lead me to this. Oh my God. We know where we are now. We now need to solve for equation. We're going to solve for variance of YT. When you solve for variance of YT, this is what we got at the end of the day. But let me tell you this. Do you know I can save you time in the exam if you don't want to go through all this? Okay, if you don't want to go through all this, please, I need you to pay attention. This is going to be in the final. Now, take a look at this. If I don't really want to go through all of this and I want to find the expected value of YT, okay, now if you have this as a specification, I need you to pay attention right now. Oh, give me 1 second. Let me first clean up. Please, I need you to pay attention right now. Now you have this guy and somebody asks you to find the mean. Do you know what we're doing here? You know what that means? You know what that guy means? It means that you use the formula. What does 0.8 represent? 0.8 C0 divided by what? What does 0.9 represent in the specification? C1. That will be C0 over 1 minus C1. Whenever they ask you to find the mean, this is the formula you're going to use. C0 over 1 minus C1. You don't need to go through all this rigorous derivation. Does that make sense? I just need C0. What is my C0? Divided by 1 minus C1. What about the variance? I'm going to go to the variance. You're also going to see, oh my God, take a look at this guy now. If you take a look at that guy, what is 0.19? The 0.19 would be the variance of the white noise, right? Divided by 1 minus 0.9 squared. Which one represent 0.9? Which one represent 0.9? That would be C1, right? C1. Then you're going to have divided by 1 minus C1 squared. Look at that. You know what? You don't need to go through all this. You only need to memorize the formula here. If I want to find the variance of YT, I need the variance of the white noise divided by 1 minus the square of a C1. And that was why I did this. I'm going to show you, before going to the correlation, I'm going to show you something. Do you see that? Do you see this? You see the formula? You don't need to do any derivation. When I say find the expected value of YT, you look at the model specification. What is your C0 and what is your C1? For the variance of YT, you need C1, then you also need the variance of the white noise. Any question on this? You don't need to go through rigorous derivation. Like I said, you make use of the formula. Now, and let me also tell you, I also want to save you time. For instance, if they give you a module and they want you to derive autocorrelation at lag 1, autocorrelation at lag 2, because of what I've done here, autocorrelation at lag 1 give me 0.9. Autocorrelation at lag 2 give this. What is 0.81? You know 0.81 means 0.9 square, right? And it means autocorrelation at lag 3 is also going to give 0.9 raised to power 3. Because of that, look at the generalization. Therefore, if they give you a module and they want you to derive autocorrelation at lag 1, lag 2, lag 3, this is the formula. You don't need to derive. Oh my God, do you see the formula now? Oh, can you see that? You just make use of the formula. All what you just need to do is to identify C1. How are you going to know C1, C0, all from your module? And that was why you need to be able to understand the module. Okay? You need to understand the module specification. Take a look at this. Do you see this guy? Do you see where you can get C0? Where you can get C1? The moment you know C1, you know C0, and you know the variance and the mean of the white noise, all what you just need to do for ARO of order 1 module, you know you need these 3 things. I'm confirming to you in my final, there's going to be a question that's centered on this in the final exam. Please take note of this formula right now. You just need to know. Now, if I ask you to find the autocorrelation at lag 1, here, you just plug in K to be 1, which is going to be rho. It's going to be rho 1. Okay. Rho 1 is going to be C1 raised to power 1. All what you just need to do is to identify what is your C1 in the module specification. Does that make sense to everyone? Okay. Now, let me tell you this. We normally say that stationarity occur when the absolute value of C1 is less than 1. Okay, if the absolute value of C1 is not less than 1, then the stationarity assumptions of AR1 module is violated. Let me tell you this. When the stationarity assumption is violated, okay, and that was why I said here, without stationarity assumption, we cannot estimate the mean. Imagine here. I'm going to tell you something now. Take a look at the first expression. If C1 equal to 1, what is going to happen? Can somebody tell me? If C1 equal to 1 in the first expression, it will break down. The denominator is going to be 0. That means I will not be able to find the mean. Not only that, I'm not also going to be able to find the variance. And that was the reason why we want our C1 at the absolute value of that to be strictly less than 1. Does that make sense? And that was why I said here, I said without stationarity, okay, without stationarity condition, we cannot estimate the mean, the variance, and the autocorrelation of the time series. Okay, now you know what I need you to do here? I got 3 different modules. I need you to try it. Show that the mean and the variance for YT will be the same for all. Try that at home based on the formula I've given you today. Okay, module 1, module 2, module 3, show that the mean is 8 and the variance of YT is 1. Okay, use the formula that I gave you today. Does that make sense? Okay, you can try that. And which formula am I talking about? I'm talking about the formula here. Can you see that? Expected value of YT equal to that, the variance of YT, and the autocorrelation. Do you see that now? So for expected value of YT and the variance of YT, you make use of that particular formula. So if you for these 3 modules, they will have the same value for mean and the variance if you tried it out. Okay, try it out. Okay. Now, this is just comparing the modules. Okay. Now, let me tell you this. We can have a situation where three modules have the same mean, they got the same variance, but that doesn't mean they are exactly the same. No. If you take a look at here, for module 2, C1 is positive, right? That will be the most smooth. The positive one will be the most smooth. Okay, in module 3, C1 is negative. That will be the most jagged. Okay, that will be the most jagged. Even though they get the same mean and variance, they are not entirely the same. And another thing that I want you to see, module 1 is an entirely white noise. Module 2 and module 3 are autoregressive module of order 1. I need you to take a look at that. Okay, so take a look at that. Okay, now how to fit a time series module to data. Okay, I think I'm going to start from here because of my time. I'm going to start from here tomorrow. Okay, for instance, if we have data set, how do we fit time series module to data? Okay, how do we compute all of this from data? For instance, take a look at me. You have data set. How do we estimate C0? How do you estimate C1? Just like what you always do in linear regression, where we fit regression model to data, how do we obtain a beta naught and a beta 1? I'm also going to walk you through tomorrow. Is there any question before I go today because of my time? Okay, so make sure you all stay safe. Like I said, I'm going to start from here tomorrow. I'm going to show you the meaning of each of these. Okay, so make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you. Have a good day. See you tomorrow.
And you too. Yeah, bye.